Today we're going to look at a couple of advanced topics in terms of centripetal motion or circular motion. Okay, so this is basically taking topic 6.1 a little bit further than we looked at it last year. Okay, in particular what we're going to be looking at is we're going to be calculating the forces at the top and bottom of the circle. The reason we're going to look at just the top and the bottom of the circle is because those are the points where our forces are going to line up, and I'm only going to have a centripetal acceleration or a centripetal force. I'm not going to have any tangential forces involved. Okay. Then we're going to look at some concepts involving energy using circular motion. And then we're going to end looking at some banking situations. Okay, these are situations where the car or plane is going to be trying to turn in a circle by using its perpendicular forces. Okay. First off, in terms of calculating forces, okay, we're still going to be using Newton's second law, okay, which says that the net force, or the sum of all my forces, is going to be equal to my mass times my acceleration. There's nothing new there. The only thing different in our situations is that our acceleration is going to be our centripetal acceleration. Therefore, I'm going to have an ability to calculate that acceleration via the formula v squared over r, or in certain cases, maybe I'll use omega squared r instead, okay? But primarily, we're going to be using v squared over r. Okay, so here's a situation, okay? I have a 0.15 kilogram coin that sits on a turntable at a radius of 35 centimeters. And the turntable rotates at a speed of 33 revolutions per minute. The coefficient of static friction between the coin and the turntable is 0.6. Calculate the magnitude of the friction force. Okay, first off, don't fall for the trap of calculating static friction via mu Fn, okay? Because static friction is a inequality, okay? It's going to be somewhere between 0 and a maximum. And unless it says something like a maximum, most likely it's placed there as a trap for you to fall in. So don't fall for it. Okay, so in our case, okay, this is what my free body diagram is going to look like. Okay, here's my coin going in a circle. Okay, the only force I have here is the force of friction. Okay, the up and down forces effectively cancel, and I don't need to worry about them. Okay, so since my net force is my friction force, I can say basically that the force of friction is going to equal my net force, or MAC in this case. Okay, and the 33 revolutions per minute given here, that's an omega. Okay, that's an angular speed that it's giving me. In revolutions per minute, I have to convert that to radians per second, yes, but I can do that. Okay, so I'm going to use this form for omega centripetal acceleration. Okay, m omega squared r. That's my friction force. And once I figure that out, I have my answer. Okay, so friction is basically going to equal 0.15 kilograms times omega, which is 33 revolutions per minute, times 2 pi radians per revolution, times 1 minute has 60 seconds, and that gets squared, and then that's going to be multiplied by our radius of 0.35, and we have to remember it's 35 centimeters, and I need to convert that. So if I plug all this into my calculator, 0.15 times 33 times 2 pi divided by, 0.15, 33, 2 pi, and the 35. I end up with a force of 0.18 newtons. Okay, so not a lot of force, but it's not a very heavy coin either, only 0.15 kilograms. Now, to be complete, I should really double check this against whether it falls within that range for static friction. Okay, so static friction max would be mu Fn in this case, or basically 0.6 times the 0.15 times the 9.8. Okay, and if I take that all together, I find the maximum friction force is 0.88 newtons. So my 0.18 is certainly within that range, and there's no problem in stating that for my friction force in this situation. Okay, so that's how we just apply Newton's second law. Okay, when I get into a vertical circle, okay, objects in a vertical circle are going to be speeding up and slowing down. So this object is going up and down like this, whereas a horizontal circle simply goes like this. Okay, so at the top and bottom of the circle, however, my forces are going to be in the vertical direction only. Okay, assuming it's a string or something along those lines. Okay, so my vertical forces are the only forces I have at the top and the bottom of the circle. Okay, when I'm at somewhere along the side, my forces are not so linear, okay? In fact, they're not. Okay, so I can't do my analysis using v squared over r because I have those two different forces at play. So that's why I'm limited pretty much to just the top and the bottom. Okay? So here's an example. I have a car going over a hill with a certain speed, okay? Any curve can be approximated as a portion of a circle, so that's what we're going to do here, okay? So in this case, my car has the force of gravity going down and the normal force going up, okay? And because it's going in a circle of sorts, okay, my acceleration in this case is also towards the center of the circle, or in this case, downwards. Okay, and that actually has a value because I'm given v and r, okay, of v squared over r, or in this case 25 squared over 200, and if I plug that in, I find that my speed here in this case is my acceleration in this case is 3.125 meters per second squared. Okay, so that's my acceleration. And my two forces must add up to my mass times that acceleration. Or basically in this case, I would have Fn plus negative Fg, negative because it's going downwards. Okay, and that's going to equal negative mac. Again, negative because my acceleration is downwards. Okay, so calculating the force of the rotor on the car, that's Fn. That's going to equal minus mac plus Fg, or basically 340 times 3.125 negative plus 340 times 9.8. And if I go through that process, I find that my normal force in this case is about 2,270 newtons. Okay, and as a quick double check, my normal force must be smaller than my force of gravity. Otherwise, I'm not going to be accelerating downwards. And 2270 is certainly going to be less than 340 times 10, or roughly 3,400 for the weight of the car. So as a quick double check, that works. Okay, example 2 is the same car, same speed, same hill, except instead of a hill, it's at the bottom of the hill now. Okay, so what's going to be different in this case, okay, not the force of gravity, that's pretty much going to be the same, not the direction for the normal force, that's still going to be up. What's primarily different here is my acceleration, again, towards the center of the circle, but it's up in this case. Okay, my acceleration is still going to be the same calculation, so I'm not going to redo it here. It's our same 3.125 meters per second squared. Okay, and our calculation is the same. Fn plus negative force of gravity is going to equal positive mac. Positive in this case because in this case my acceleration is going to be upwards. Okay, so doing some algebra, I find that Fn is going to equal mac plus the force of gravity, or basically mac plus mg, or simplifying m of a plus g. Okay, so doing that calculation, okay, I basically would end up with 340 for the mass times 3.125 plus the 9.8. And if I do that calculation, I would basically find that my normal force is larger in this case, as expected, 4,390 newtons, roughly. Okay, if I take it to significant digits. Okay, so in this case, 4,390, my normal force should be larger than my force of gravity, and it is. Okay, so that's how we're going to do our analysis at the top and bottom of the hill, okay? In fact, these types of problems are really nothing more than our elevator problems, okay? Because I just have two forces, one up, one down, you know, in this case, and an acceleration that's either up or down. Similar to what we have for those elevator problems. The only difference is how we calculate acceleration. Okay. So another aspect that I have with objects that go in a vertical circle is that I can't calculate velocities at the top and the bottom without, the easiest way of doing that is through conservation of energy. Okay, because at the top of the circle, I'm going to have GPE and KE. Remember, it's higher, so it's going to have gravitational potential energy, and it must still be moving. If it's not moving, it's going to fall straight downwards. Okay, it's moving horizontally, yes, but it's still moving. Okay, and at the end, okay, all I'm going to have at the end is the kinetic energy. So I can calculate the speed at the bottom or at the top as long as I know the height that's involved and the speed at the other location. Okay, so here's an example. Okay, I have a 5-kilogram bucket of water twirled in a vertical circle of radius 0.7 meters. What is the minimum speed that the bucket must be spun so that the water stays in the bucket? Okay, similar to the car problem, but this is one of those min-max types of problems. Okay, for circular motion. Okay, so at the top, I'm still going to have force of gravity, but I'm also going to have force of tension going down and an acceleration going downwards. Okay, and all of those things must match up, but I'm looking for a minimum. Okay, so I'm going to define downwards to be the positive direction because all my forces are downwards in this case, and I can ignore the minus signs. So force of gravity plus force of tension must equal my mass times centripetal acceleration, or mv squared over r. Okay, well, as my speed gets smaller and smaller, okay, as this thing goes down smaller and smaller, the left side of my equation, okay, must also get smaller and smaller. But the force of gravity is fixed, okay? It's just mass times that 9.8, mass times g, every single time. It doesn't change. So what changes is my force of tension, okay? This goes smaller and smaller until it gets to 0, okay? At 0, it can't get any smaller because if it goes negative, it's implying that my tension is pointing in the negative direction or upwards, okay? And strings can't push. They can only pull, okay? So the smallest value for tension is 0. So I'm actually going to stick in 0 for that. Force of gravity plus 0 is going to equal mv squared over r, okay? Or basically mg is equal to mv squared over r. My m's cancel, and then v squared is equal to gr, or basically my minimum speed is the square root of g times that radius r. Okay, that's all we have. Okay, and I like to keep my letters until the final end because the formulas, as you do enough of these problems, you get more and more comfortable with the formulas. And when you see that formula again, you're then kind of get a warm fuzzy feeling that you're on the right track. So try to avoid sticking in numbers until you get to your final solution. Okay. So in this case, this is the square root of 9.8 times my r of 0.7, and that turns out to be about 2.6 meters per second, just meters per second. Okay, So that's kind of a min-max analysis. But the next one says, what speed does it have at the bottom, and what is the tension in the string when it's at the bottom? Okay, so all of a sudden, okay, I have to calculate something at the bottom when I can only figure out a minimum speed at the top. Okay, so we did figure out that minimum speed. Okay, that minimum speed at the top happens to be 2.6 meters per second. Okay, but it also has an h at that point of twice the radius, or 1.4 meters. So I'm going to have an mgh at the top and a 1/2 mv squared at the top. And at the bottom, I'm going to have a 1/2 mv, I'm going to call it b squared. Okay, no gravitational potential energy at the bottom. So I can figure out the speed at the bottom via conservation of energy. I can't do forces unless I, really start to apply calculus. And I can't do kinematics necessarily because my acceleration is not constant. It's changing directions all the time, and it's also changing in magnitude. Okay, but I can do conservation of energy. So in this case, my m's are going to cancel, so I don't really need that. Okay, so I end up with 9.8 times 1.4. Okay, my h, remember, is twice the radius, plus 1/2 2.6 squared, and that's going to equal 1/2 VB squared. And if I plug that into my calculator, I find VB is going to equal a speed of 5.9 meters per second. Okay, faster as I would expect. Okay, faster than the top. Okay, what is the tension in the string? Oh, hold on, that's a different question now. Okay, so but I know a couple of things. Okay, this is again the same thing as the car problem. Okay, because when it's at the bottom, I have the force of gravity downwards, force of tension upwards, and my acceleration upwards. Okay, and I can calculate that acceleration because that acceleration is going to equal v squared over r, and here's my v, and here's my r. Okay, and then going through the motions again, ft plus negative fg is going to equal mv squared over r, and then ft is going to equal m v squared over r plus mg. And plugging that into our calculator using numbers, I'm going to skip the numbers because I'm kind of running out of room. But I have 5 times 9.8 for mg, 5 times 5.9 squared, divided by 0.7, add those together, and I find that my tension at the bottom is actually pretty high, and it's roughly 298 newtons. Okay, hopefully I got that right. $298. Okay. So that's how we would do an energy analysis. Okay, you have to be able to think of the fact that it's at a different height at the top versus the bottom. Okay, and then we simply go quickly into conservation of energy to figure out what the speed of the bucket at the bottom is. Okay, so work is an aspect of energy, and you may wonder, why can't I do conservation of energy? I have an external force acting on that bucket, the force of the string. Okay, but that force of the string, okay, is going to be perpendicular. That force of the string is radial. It's straight towards the center of the circle. Okay, whereas my displacement, okay, is still tangential, and there's a 90-degree involved between the force and the displacement. And if you remember the formula for force, for work is force times distance times the cosine of theta, or in other words, the dot product of the force vector and the displacement vector. Since they're perpendicular, cosine of theta is 0, and so the string actually does no work on the bucket. Okay, that the work that it does, okay, is zero, meaning the bucket is that string is not responsible at all for changing the object's kinetic energy. Only gravity is. Okay, and that's why we can do a conservation of energy analysis. Okay, so the last subject I want to talk about is banking. Okay, banking is not the financial situation. Banking is what happens when you have a slanted surface, okay, an inclined surface to help you make a turn. Okay, for cars, it's basically the road surface is banked. You'll see that on exits, or if you watch some car racing, NASCAR type stuff in the Indianapolis 500, you might notice that the road is actually slanted at the curves. The reason it's slanted is to help allow the surface of the road to help the car make the turn at a higher speed. Okay, for the IB, we don't need to calculate that, but we have to understand qualitatively what's going on in that situation. Why does the car make a turn? Where's the circle? Where direction is that acceleration? For higher level physics, okay, yes, we're going to need to do that calculation, and we might do that calculation later in school. Okay, but in this case, if you look at the first picture, okay, of the car, okay, this picture under A, there's no slanting, okay. The only force that lets me make this turn is the force of friction between the tires and the road. Okay, it's actually static friction, but that's a different story. Okay, whereas in situation B, I have two forces. Again, the center of my circle is still horizontal. It's still a horizontal circle. My acceleration, therefore, is going to just be this, okay? The force to the right, okay? What forces are pushing it to the right? I have both the normal force, a portion of my normal force, and sine theta. Okay, that's what this is. And a portion of my friction force, or F cosine theta. Both of those forces are pushing me towards the center of the circle. Okay, and because I have those two components, okay, in particular, n sine theta can be significant. Okay, so I can make that turn at a higher speed than if it was just friction. Okay, because my v squared over r, okay, can now be bigger than it was without banking. Okay, for the IB, we primarily look, they like to look at planes, okay? Planes don't have a surface, but when they want to turn in a direction, okay, they tilt their wings so that the lift, okay, the green vector shown in the picture, okay, the lift of the wings, which normally helps them fly, now also there's a component of it, okay, lift sine theta in the picture, that's pointing towards the center of whatever turn they want to make. Okay, so in this case, the yellow force in the picture is the net force. Okay, that's the centripetal force. Okay, so planes are easily turned by simply turning their wings, tilting their wings, I should say, and that forces them to turn one way or another. Okay, in this case, my force vector is to the right, which is pointing towards the center of the circle. Therefore, this plane is turning to the right. Thank you.